So today we'll just be looking at the gamma distribution and its relationship to the exponential distribution. We say a continuous random variable x has a gamma distribution with shape parameter a and rate parameter lambda if it has the following PDF, where f of x is lambda to the power of a over gamma a times x to the power of a minus 1 times e to the negative lambda x, when x is greater than or equal to 0 and 0 everywhere else. And we also need a greater than 0 and lambda greater than 0 for this to be a valid PDF. Now, if you've never seen this weird thing right here before, my gamma a, don't worry, just pause the video and take a look at my video on the gamma function. I'll leave a link in the description below. There's a lot of good resources on this. It's pretty much just an integral. Otherwise, you guys know the drill, right? I'll just draw your attention to a few things here. First, notice that we are 0 for all negative value of x. And second, I should say that we usually use the gamma function to model data with skew, as you can see by this graph and this weird part here. So yeah, we'll just jump right into it. So I get that, you might be disappointed that there's no closed form here. But really, there is a semi-closed form for the CDF of the gamma distribution where you define, integrals as functions, and it ends up being a bit weird. But you can find that online. There's a lot of resources on that. But it's not really useful for our purposes. So instead, we'll just leave the CDF as is. And I'll just draw your attention to two things here, right? Notice that our CDF is 0 for all negative values of x, just like the PDF. And also notice that this guy right here, he's just coming from the definition of CDF. There's nothing new here, right? This is just directly from the definition of CDF. And next, I'll walk you through how to find the expectation, variance, and the MGF of this distribution. So if you'd like to give those a shot, just pause the video here. Otherwise, we'll just move on. The expectation of the gamma distribution is just a shape parameter divided by the rate parameter. So in this case, it's just a over lambda. And you'll notice here, right, all I'm doing is restating the definition of expectation and stuff. And this is our PDF. So there's nothing really tricky here in our integral. The only thing that you should take note of is we're just using the property that gamma a times a is gamma a plus 1. So that's how we get here, right? And then we're also using the property that this integral right here follows gamma with parameters a plus 1 and lambda. So this guy has to integrate to 1. And that's how we get this here. So our variance is a over lambda squared. And now that you see that, you may start to see a pattern here with how it relates to the exponential distribution. Either way, let's just quickly look at this integral here. You'll see that we're using the same trick as last time. There's nothing new here, right? We did this in the expectation slide a minute ago. And really the idea is just to use the properties of the gamma function. So in this case, the fact that gamma a plus 2, right, equals gamma a times a plus 1 times a. And then, right, you're just multiplying by 1. Like, there's no magic here. And your goal is to make this integral over here follow some sort of gamma distribution, right? And once you get that, since we're integrating over 0 to infinity, we know that if we follow gamma a plus 2 lambda, like we do in this situation, this guy integrates to 1, giving us him. And then this step is pretty straightforward, and then you're just subtracting. So this integral is a bit trickier than the last two, but it's still not too bad. All we're doing here in the first step is we're just moving the constants out and simplifying our e to the power of whatever, right? That's all we're doing here. And after that, right, we're just doing a u sub where u equals x times lambda minus t, right? Which is how we got this guy. We're just plugging in, you just rearrange for x, and then you plug that in there. And it's also the same reason why this is negative. Because here it's x times t minus lambda, but our u sub was u equals x times lambda minus t, which is why we have the negative here, like I said before. So then after that, right, we're just moving our lambda minus t's out, these guys. That's how we just put them here. That's all we're doing. And then you'll notice, right, this guy is our gamma function from the previous videos. So, you know, gamma times gamma cancels out, right? And then this is just, you know, I'm moving the a out, but this last part here is pretty straightforward as well. If you've been paying attention, you may have noticed the relationship between the expectation variance and MGF of the gamma and the exponential distributions. If you haven't, right, that's all right, but you should probably review the exponential distribution before moving on. And here I'll just show you the two big results. So first, if you have a gamma distribution with shape parameter 1, then it's just an exponential distribution with a rate parameter lambda. And this result's pretty straightforward, right? It's just algebra. It actually just simplifies out to that. The only thing I'll point to here, right, you'll remember from the gamma function video that this is a minus 1, so here we have 0 factorial, right? That's where this comes from. And the second result is that if you have a gamma distribution with shape parameter k, then it's just the sum of k exponential distributions with rate parameter lambda, and the other way around is also true, right? So our second result, you'll see this here, right? This is just using the properties of MGF, and that's pretty easy to prove, right? So you'll see that our second result tells us what the gamma distribution is usually used for. And that's just modeling the sum of k exponential distributions. So in a moment, I'll let you take a look at the practice problems I've written up. But for now, you know, take as long as you need to make sure you understand this slide. Here I've provided some practice problems of varying difficulty, and I really do encourage you to give these a shot. But yeah, you know, thanks for listening. Feel free to ask your questions in the comments below, and please do let me know if I made any mistakes at any point in this video. I'll see you guys next time.